That's it from me this morning. I would like to hand over now to our first talk of the day, Mr. Andrei Krutikov from Noeon Research, who will tell you about Noeon's approach to safety.
Andrei, I'm CEO of Noeon Research. Noeon Research is an R&D company that is trying to find an unconventional approaches to an AGI. Notable features of our approach are representing goals and purposes as first-class citizen objects, and also representing knowledge in discrete manner. But what is knowledge? So we tend to say that knowledge is anything that agent decision-making procedure can condition of. It is a broad definition, so let me focus on types of knowledge. So what types of knowledge exist? We divide the knowledge in two categories: factual knowledge, or know-what knowledge, and procedural knowledge, or know-how knowledge. One might think of latter as capabilities. Now let me talk about our operational definition of interpretability. We consider a system to be an interpretable one if operator can exactly locate where knowledge that is influencing observable behavior is stored, and second, operator can change system's knowledge in a manner that is predictably changing the behavior of the system. Of course, the second one can be only done by using some tools, and it will require some operator training. Interpretability, of course, is important for AI because, well, interpretability allows us to assess capabilities of the systems so we can control them. Also, if we want to perform some manual intervention, we also need to know where to perform this intervention. This all is needed to establish trust to the systems that we build. So now let me talk about existing solutions that are there. So of course, there is a symbolic good old-fashioned AI. And in good old-fashioned AI, we store factual knowledge and procedural knowledge separately. Factual knowledge being stored in knowledge graphs or knowledge databases, while procedural knowledge is external solvers, external kind of reasoning engines. Is it interpretable? Yes, because one might locate inside the knowledge graph the precise location where, let's say, relation triplet is located. Is it corrigible, though? Well, modular the external procedures. One, of course, might change something inside the knowledge base, but it's difficult to change algorithms. Now, large language models store both factual and procedural knowledge in the shared space, in the shared weight space. Are those interpretable? Well, with clever tricks, yes. Is it corrigible? Prohibitively expensive. The retraining cost is high. Now, our solution, akin to LLMs, store factual and procedural knowledge in the same semantic space. However, this space is represented via discrete structures rather than weights. So it is way more legible. And I dare to say that it is both interpretable and corrigible. We are building a system that is interpretable by design. In addition to discrete representations, we develop inspection tools that we consider as an essential part of the whole system. Those tools help us interpreting systems in hierarchical manner on several levels of abstraction, or as we call them, language levels. So language level 0 is the fundamental level at which all our stuff is stored in discrete structures, namely in partially ordered sets, also known as directed acyclic graphs. They are enriched with some structure, like maybe embeddings or labels or user data. And information retrieval from those structures is done via what's called subgraph isomorphism matching problem. And if one wants to put new information inside this graph, one has to perform a graph transformation. Also, any reasoning that is happening inside our system is also done via graph transformations. That's the screenshot from our internal tool. This is the tool we use for something we call surgery. We perform this surgery on graphs, so we have very detailed view on what's going on inside. On the left side, you might see the smaller pattern that is recognized in a big graph. Then, language level 1 is the level at which we talk about executables and execution trajectories. At this level, we store procedural knowledge in explicit form, and this is the level where we get our transparency over inner workings of any reasoning process that is going in our system. Again, this is a screenshot of the tool that we use to deal with the language level 1. You see there's a bunch of rectangles representing calculations, and they are patched together with control flow links and data dependency links. Now one might ask, well, where is the factual knowledge inside the language level 1? The answer to that is this. We consider a factual statement to be a statement insofar as this statement is about computation results. So, in other words, when we talk about something happening in outside world, we're talking about this in terms of some process in outside world, some computational process in outside world, ended with certain result. So it is natural for us to represent facts as short sequences of trajectories. Now, language level 2 is the level at which we have ontologies, models, goals, agency in explicit form. This is also the level at which we deal with operator input. This is the level at which we elaborate operator input. Also, this is the place where we identify the lack of required semantics that is needed to perform the user request or answer user's question. Again, this is a screenshot of one of our tools that we use. Here you can see the textual input, which is then parsed into entities, some of them grounded, some of them not. The very same input then represented as invocations, so language level 1, procedural kind of knowledge, and presented to the operator in this form. Now, do we have parts that are not interpretable? Well, of course. For instance, the subgraph matching that I mentioned before is an NP-complete problem, so we have to use some heuristics and some help from machine learning models that speed up this information retrieval. Also, the user input, to make it more user-friendly, we might also deal with natural language processing. But those models, they are small, compartmentalized, and trained separately. So we consider them to be safe. This design choice also reflects the fact that we are not entirely happy with big models, with machine learning. So what we believe is that it is possible to build systems that are safe by design. No need to be reactive to large language models. We might want to build new architecture from the scratch, and that's what we do. So I think it's important to say that inspection tools are essential part of the system, because we do not consider our system to be finished unless we have those inspection tools. And also, I believe that the most important things like goals and beliefs and conclusions and capabilities should be first-class citizen objects. This concludes my presentation, and I welcome your questions. Thank you.
How do you make sure that this remains interpretable as you scale up? Like, program induction methods can induce programs with like hundreds of thousands of invented predicates, and those invented predicates aren't necessarily themselves interpretable.
Right. So I think the key thing here is that we structure the knowledge in hierarchical way, So our tools actually allows us to choose arbitrarily abstract level of considering things. So if one wants to deal with very large objects, very large, I don't know, trajectories, very large bunch of conclusions and reasoning process, one might. But also without, like, one is retaining the ability to actually drill down and look for details on demand. So that's how we can be sure that any part of the system is still inspectable.
Thank you for the talk. This is actually an interesting direction. At level 0, you mentioned that you're performing a subgraph isomorphism problem, which is known NP complete. This would seem pretty untractable for really large knowledge graphs. What are you doing to address that? Right.
So it is indeed an NP-complete problem. So as I mentioned, we utilize some ML models that help us with this isomorphism problem. But it's not just that. Of course, in general sense, there is no free lunch theorem, so we cannot guarantee good times for any subgraph matching request. However, in our case, our graphs are not random. They have very specific regular structure. So because of those regularities, we might utilize them to fasten up our search. Also, there is one have to understand that this isomorphism problem is not purely an isomorphism problem because we already have some parts of the request or some parts of the request graph matched. Because whenever a person asks a question, inside this question there are already known parts to the person who is being asked. So those are our kind of pinpoints.
Do you have like a garden path problem though, where you find a subgraph of a subquery and then you have extra data come in and the subquery stops matching? You have to like redo it from the beginning again.
Yes, the subgraph matching process is interactive in a sense that if we notice that, okay, this is taking too much time to find an answer, we might interrupt this process and ask user for clarification.
All right, thank you very much.
It's very interesting. How's it going? Any benchmarks? Any like how far along do you think you are? Are you gonna get us AGI next year? 5 years?
That's a good question. I think our immediate plans is to build proof of concept within this year. I would say we are still in the intense research phase. So I already showed you some screenshots. Those are real. Those are from our tools. So I would say at this moment we are almost done with the knowledge representation part, and right now we are looking into external reasoning procedures.
So how does knowledge get into the system?
Right. So this is a really good question because in good old-fashioned AI we know that there was a problem with initial population of the knowledge bases. So in our case, there is no distinct kind of training stage and inference stage. The system trains and learns stuff online from the user input. So imagine if user asking system to do something, and within this request, user mentions something that system doesn't know. This will lead to the process that we call elaboration, and this elaboration process will ask user about the required semantics, so the required semantics will be extracted from the user. Of course, when I say extracted from the user, I don't mean that the system will ask everything from the user. It is also possible to feed in, let's say, a textbook on JavaScript or something like that, and the system will be able to kind of consume it. But basically, at the situation where we have a lack of semantics, we are requesting that from either user or environment.
That's a question for myself. Not the live stream, unfortunately, but so in transformer architectures and in ML, we've got a dictionary, and then we train the model, and we store the result in positional embeddings that in an arbitrary large space they set the words around that we just cannot imagine with our brains. So how do you solve that with the knowledge and ontology representation What's the approach?
Right. So I think one of the metrics of how big or how capable the LLM is its size. In our case, the size doesn't tell you much because you might have a very, very big graph which is regular, like every node has the same degree, and in that case, this graph won't contain too much information. So what we can do though is to expand this graph with some kind of interesting topology, interesting geometry, and looking at that geometry, we can find a place where to store that information. So I wouldn't say that the limitations of the architecture, LLM's architectures, are applicable in this case.
Cool. All right. Well, thank you.
Thank you very much.